Good morning, good afternoon, good evening, wherever you happen to be in the World Wide Web. This is John Tuigo. I'm the chairman of the Data Management Institute, and I'm the guest today of Starwind Software, who've asked me to come and give a brief presentation on NVMe and the prospects for an all-silicon storage infrastructure. That's a term I hear a lot these days when I walk into certain client sites. Everybody seems to be very keen to go to all-silicon if possible. So let's take a little bit of a look at this for the next few minutes and see what we can learn about NVMe. First of all, I'd like to, again, thank Starwind Software for inviting us to give this presentation. What we're here to discuss today is NVMe. To those who aren't in the know, that stands for Non-Volatile Memory Express, which is actually kind of a shorthand moniker for non-volatile memory host controller interface specification. That's a mouthful, so you can kind of understand why they went to NVMe instead. Basically, what most people who ask me about NVMe want to know is what is this technology, what does it enable, what problems does it solve, and how might it be valuable inside my data center? Now, like most things, it's a technology evolution that's filled with politics, and because it has mostly to do with flash memory-based storage, it's a topic that usually requires a bit of effort to separate the magical thinking from reality. And I say that sort of tongue-in-cheek, but actually very factually. We've all been through sort of a first wave of flash technology marketing, most of which proved to be filled with, let's say, uncertainties and maybe misrepresentations. And flash was actually on its way to kind of falling out of favor with the community. We'll get there, but later on, though, when NVMe hit the streets, it sort of reinvigorated the whole discussion of flash. So this presentation is going to provide a starting point for those who are just getting started with flash and who want to learn a little bit more about the development of silicon storage to see what value it might have. Now, as I said, NVMe, or Non-Volatile Memory Express, is really a description for a new host controller interface specification for flash memory-based storage. NVMe Express, according to the NVMe.org website, is an optimized, high-performance, scalable host controller interface that's much streamlined over what we had before. It has a streamlined register interface, a streamlined command set, and it's really designed, according to its purveyors and advocates, for enterprise data center and client systems that use flash storage. Okay, now the backstory on this is you have to actually go back to sort of a brief history of flash storage. The original memory-based storage, or SSD, is actually very old. It dates back almost to the beginnings of contemporary computing. But flash itself was developed by Toshiba from electrically erasable programmable read-only memory, or EPROMs, to those who used to be into taking the tin off the back of the server and playing around with the components in the back. In the early 1980s, EPROMs were these very large memory chips, and they were programmed with a particular set of instructions, which they held that particular programming code for a period of time, and they would just replicate or repeat the functions that they were assigned to perform. Now, there were really two different flavors of early flash storage. There was NOR-type flash, which could be erased and rewritten at the level of an individual byte, and then there was NAND type memories that could be written and read in blocks or pages, smaller than the entire memory device, but still larger than an individual byte. Frankly, because of their lower price, the NAND type memory was pressed into service and became what we contemporarily call flash memory. But, flash had both its strengths and its weaknesses. First of all, it was presented initially as an alternative to hard disk drives. Theoretically, it was going to be more durable than disk. There really isn't enough empirical data to prove the life expectancy of flash, but flash is supposed to be a non-volatile memory, which means you write your data to it, and even if you lose power, the data remains. And the idea was that, the way you stored data on flash, you should be able to hold the data in the flash drive, even powered off, for 30 years or more. Those are some of the retention claims that have been provided by vendors. Of course, most of these claims are untested because flash hasn't been in the market for 30 years in its current value. And we have many instances due to manufacturing defects or other kinds of firmware problems of memory leaks where flash did not prove to be quite as durable over a period of time. Now, it is more energy efficient than, say, magnetic media like disk, which has lots of moving parts and motors and so forth. It tends to be a lot lighter physically, so it finds its way into mobile devices, portable computers, and tablets and smartphones and the like. And it has a small form factor, which of course also plays into that. And according to the various vendors, it's 5 to 10 times faster reading data than a hard disk. I would say that today, with the advent of 3D NAND, you probably are going to see claims of up to 50 times faster than a disk drive. And that supports the idea of selling this more expensive storage capacity at a substantially greater price than what you'd pay for a magnetic device, basically supporting the idea of paying for the IOPS that you're getting, the input-output instructions per second. However, at the end of the day, for those of us who don't have bottomless bank accounts, it's still flash is still way above the cost of a hard disk from a capacity standpoint. So price per capacity, hard disk wins, but in terms of at least at the base level, there are even some arguments to be made that at scale, the power cost savings that you're getting with flash will offset the price differentials between the components themselves. So it's worth a look. It has kind of an interesting matrix of costs and proposed benefits. Now, there are foibles with flash, and of course the industry has tried to play those down to the greatest possible extent. They want to sell the technology. One of the big ones is memory wear. I think we've been hearing reading articles about this for probably the last decade or so. Cells, the locations where data bits get written in flash, have a tendency to wear out after a certain number of times that they've been written. The number is a matter of hot debate. The rule of thumb has usually been that about 250,000 writes per cell location in an MLC or multi-layer cell device it will burn out cells. And what happens when a cell burns out? Cells are organized in a flash chip into groups, and the entire group needs to be invalidated when one of its cells fails. Now, that simple fact has kind of led to a lot of interesting engineering directed toward extending the useful life of those cells. But until we come up with better strategies for reinforcing and improving the capabilities, I mean, we have ways to do it. There's a way to reheat and re-engineer the cell in place by superheating a coil or a wire inside the cell after a certain number of writes. That technology is very expensive. It hasn't been implemented yet. It would take quite a rehoning of the manufacturing assembly lines in order to bring it online. But there are ways to rejuvenate a cell, and it just would increase the price of the solution. So instead, what we've basically seen a lot of focus on is what I call spoofing, which is buffering and working around and wear leveling technologies, you may hear them called. It's basically, one approach is to advertise a certain amount of capacity on a flash device, but actually have a lot more capacity than that, a bunch of spare groups of cells, and then having some interesting controller logic that will flip out a cell or a group of cells at different periods of time so that you can give certain groups of cells a rest and maybe erase them in advance. The other problem with flash is that it tends to decrease in terms of its efficiency and its speed of writes after the first time it's been written. In fact, it loses 50% of its performance once you've fully written the flash device, because the next time you write to a group of cells, you have to delete all the data that's in that group, before you can write new data to the group. So that's a two-stage process, and that reduces the efficiency of the flash device by about 50%. Anyway, through all these wear leveling techniques and these interesting controller designs, folks have been trying to work their way around and sort of spoof those problems so they're not as in your face as you might think. And fragmentation is another issue that folks have been writing about a lot recently. Some data may be lost because of file systems that aren't really optimized to use flash. And this is a focus of a lot of presentations at convocations like the Flash Memory Summit. You'll usually see 9 or 10 presentations from various vendors who are trying to come up with a better file system for Flash. So the bottom line is that there are foibles in Flash, but you very rarely hear about it because vendors have a tendency to drown out the noise with a lot of architecture that goes over the top of the architecture, and a lot of original offerings as well. Now, there were early growth pains, as I alluded to at the outset. The early commercial silicon disks or flash-based disks were basically emulating a hard disk, and they used a SATA controller, the serial ATA specification that's been used to do quick connections of disk devices primarily to a computer bus. SATA controllers were very convenient because they existed in just about every machine when Flash hit the market about a little less than a decade ago in earnest. And but the problem is that they're controllers for hard disks, and they aren't terribly efficient necessarily at handling the capabilities or exploiting the capabilities that are in flash devices. The maximum bandwidth, for example, of SATA controllers were well below the potential interface bandwidth of NAND SSDs. SATA controller, for example, offered 560 megabytes per second as their bandwidth versus an early 4-chip SSD with a combined potential interface speed of 1.6 gigabytes per second. So in some cases, several orders of magnitude difference between what the potential was for moving data to a disk device versus moving data to a flash device. And if you're not supporting that, chances are at some point, if you're delivering data faster than as fast as the SATA bus will permit, you're not going to be driving your flash devices at its rated speed. Plus, there was an encoding overhead. These were buffers and registers and things that had to be accommodated in disk electronics in the logic center of an SSD controller that really aren't necessary with flash at all, and they were costing an additional 20% of the bandwidth that was available with the SAS bus. And SATA bus. The SATA controller itself was designed to buffer data writes at many locations that intended to basically adjust all and match all the speeds and provide a buffer so that you could write data to a disk device faster than maybe it was actually able to take. It would temporarily store in a buffer while it was waiting its turn to be written onto the disk media. And that was very essential for disk drive connections to your computer, but not necessarily as important for flash connections. And these additional buffers have added even more latency to I/O. So there were some good engineering reasons for looking at the replacement of SSDs, or rather the replacement of a SATA controller to connect SSD technology to a computer. No doubt about it. And it gave a lot of flash vendors a context for developing a lot of proprietary software stacks and specialty drivers to go with their products, and they could brag about their stack and their driver being more efficient than their opponent's stack and its driver. But that was basically a two-edged sword. When you think about it, all that additional technology created a wild, wild west in the world of flash. There was a lot of interesting engineering, but some vendors were leveraging that engineering to lock customers into their technology and lock competitors out of their technology. So, if the customer standardized on company XYZ's SATA approach, they basically had to buy all the products for anything that was going to be a part of that kit from the same vendor who was offering that particular proprietary stack. And it drove up the cost of flash products over time, and it drove down the enthusiasm for flash storage generally. I had one client that was a very large credit card processing company, and they asked me to consult on a flash purchase they were thinking about making. This is 5 years ago, 6 years ago. And what we discovered was, because of the wear rate on the product that they were considering and the number of transactions they do per second, over 1 million a second, that they would probably be replacing these $40,000 flash cards every 30 days, if not sooner. That was going to be very expensive. They're going to lose all the money while the system was down doing the replacements, and of course the cards themselves were not an inconsequential cost. So at the end of the day, that looked like it was a non-starter for them. And I think a lot of companies came to that conclusion, especially since it happened, the advent of flash kind of corresponded with the dawn of the Great Recession, and companies were being a little more circumspect about what they were spending money on. So companies were trying to avoid lock-ins, and that kind of squelched the early enthusiasm that there was around flash technology. Now, the banner event, or the game changer, happened, if you look at the recent history, at the Intel Developer Forum in 2007. Now, there was a intolerance among companies to go to brand X flash vendor and dedicate themselves to that vendor's approach for proprietary engineering around flash. However, there was one company, probably more than one, but in this case one company that consumers had for a long time trusted to provide single source technology, and that was Intel. Their CPUs and their chipsets were integral to just about every server and computer since they were introduced with the 8086 chip architecture back in the late 70s, early 80s. So, basically Intel walked into this market where they saw enormous potential opportunity for growth, and kind of this Wild West environment of vendors competing against vendors for the differences in stack engineering. And they said, we're going to drive a standards-based approach. That sounds wonderful. They were going to put flash storage technology into the market that would force the proprietariness of stacks and drivers out of individual components. They were going to embed a common stack on Intel chipsets, and they're going to operate them from there. That sounded like a godsend to an awful lot of people. Frankly, if I had been an investor in any of those third-party developers in Flash, I should have pulled my investments at that point, because obviously the 800-pound gorilla was coming in and more or less taking over the industry at that point. Now, the NVMe initiative began, and at that point, and other developers began to throw in with Intel, and basically that's where we got to with NVMe coming to market. Basically, their goal was to provide a PCIe interface for flash modules, a way to directly connect flash to PCIe bus that exists in most smaller computer systems these days, and that would eliminate the need to use the SATA controller and all of those proprietary workarounds we discussed earlier. Now, their primary goal really was to attack bottlenecking, which is what the name that was given to the kind of the throttle or the latency-inducing characteristics of a SATA bus controller, by expediting storage I/O processing. Now, the PCIe bus enables several capabilities that SATA did not have. For one thing, SATA and SAS supported 256 commands buffered up into, and 32 commands for SATA, buffered up into a single queue, and you'd basically stack up all your commands in that queue, wait for them to be processed by the device that was connected to the SATA controller. With NVMe, you've got 64,000 commands per queue and up to 64,000 queues. So the idea was we were going to broaden and deepen the queues that were available and the queuing capabilities, hopefully to expedite and parallelize, if you will, create in a parallel fashion the execution of storage I/O. Now that also came along with eliminating I/O locking. We had to lock one set of queues with SAS or SATA while we executed another, and then we could unlock the next set of queues and so forth and so forth and so forth. That got to be kind of a troublesome time-sharing experiment. With PCIe, and NVMe, we're hoping to eliminate that locking altogether, and also to do interrupt steering, which was going to hopefully reduce some of that other latency that accrued to the SATA bus. Now, at the end of the day, what was produced was a standard that uses half the number of CPU instructions to process an I/O request than did SAS or SATA. And that resulted in higher IOPS per CPU cycle and lower I/O latency in a host software stack. All right, that all sounds great. I mean, it doesn't really solve all the problems of storage. It doesn't really make everything go faster. But if you were encountering a log jam where you were overloading with traffic the capabilities of the SATA bus controller, then this was a workaround, and at least it was standardized. It was something that Intel was going to support on every single one of its chips. So a better SSD? Well, yes, no, maybe. The pitch here is that NVMe, and this is a quote again from early documents from NVMe Express, NVMe was architected from the ground up for non-volatile memory. Okay, it isn't using a disk device controller and substituting what's behind it. Instead of a disk drive, use a flash drive. This was built only for flash. And NVMe Express significantly improved both random and sequential performance by reducing latency, enabling high levels of parallelism, all those queues, and streamlining the command set while providing support for security, end-to-end data protection, and other client enterprise features that users say they need. Now, NVMe Express provides a standards-based approach to enabling a broad ecosystem adoption and PCIe SSD interoperability. Now, when you read between the lines here, what they're basically saying is, look, we've standardized this stuff now. Everybody can sell the same kind of product, and you can basically swap between different kinds of products, and you're probably going to get a faster performing flash memory-based storage device as a result of this, with lower controller latency, less software latency, and of course no drive latency, because you've eliminated the electromagnetic properties of mass storage. All right, now the truth be told, NVMe may be a solution that's still in search of a problem. And I say that not just tongue-in-cheek. I mean, basically, the acceleration of storage I/O is being presented as sort of the Holy Grail. This is where magical thinking comes into play. Your virtual machines are all going to work faster. Your in-memory databases are going to work better. Well, the value in terms of virtual machine performance is, of course, very questionable and very system-dependent. The cause of a slow-performing virtual machine rarely has anything to do with storage I/O. I mean, I wish that people would get this out of their minds. I know it's promulgated by some of the leading hypervisor vendors, but it simply isn't true. If you look at any system, whether it's a NVMe system or a SATA system, or using flash or disk or whatever, typically when you've got a slow-performing VM and you look at the causes for that, if you throw a meter on it, you're going to find that you have a very shallow queue depth. That means that there's no logjam, no choke point, no throttling of I/O going to the storage device at all. That your problem is somehow upstream from storage, that your virtual machine is performing terribly because of something that occurs earlier in its processing. And usually that has to do with the fact that we're doing sequential threading of all I/O out of a chip. That's an inherited characteristic of unicore chip designs, which now find their way into multi-core chip architecture. So we're not unloading I/O efficiently from the application to begin with at what we call the raw I/O end of the equation. There are ways to do that. You can go look at Google it if you want to, look for parallel I/O. You'll find some other approaches, but that's really where the logjam is in most cases for VMs, and frankly NVMe does nothing to adjust that or change that. Okay, now there are benefits to NVMe. I'm not going to disagree with that, but I don't see necessarily expedited VMs as being a benefit. Now, the other side of this, a value to in-memory databases, there we may have some potentially greater value, but only if an in-memory database is actually created to leverage NVMe technology. Hopefully, this is a case of field of dreams, where now that we've built the NVMe protocol, the industry will come to it. NVMe by itself does deliver a net overall reduction in latency over SATA attached SSD, but flash is still not optimized for writes. In fact, people who think that they're going to get really fast data capture out of flash, it is substantially faster, of course, than a disk drive, but it's slower than DRAM. Standard RAM in a system is much faster. It writes fast. It's not non-volatile, but it writes fast. SSDs, however, do not. Flash is not known for its write capabilities. It creates a wonderful read buffer. It's not necessarily optimized for writes. So the key value needs to be seen in this technology as an enabler for future architectures rather than the sort of an end goal in itself. For example, you hear a lot about hyper-converged infrastructure right now, HCI. What is HCI? It's basically taking a server and some storage directly attached or internal to that server, plus adding a hypervisor and then a stack of software called software-defined storage, and cobbling that all together in advance into an appliance, so that basically we've got as a compute model that's optimized for virtual machine hosting. The server hosts the application in the hypervisor space, and the hypervisor controls all the storage resources via a protocol stack that's been developed just for that particular kind of hypervisor. Now, that's the game that many companies are in today. In fact, some very nice software-defined storage stacks and hyper-converged appliances are available from our sponsor today, StarWind Software. An interesting model. Now, NVMe could enable greater density of storage inside a hyper-converged infrastructure appliance. Could make it much faster, in terms of its overall operation, and much lower latency. Now, if anybody should need this, again, VMs aren't necessarily going to be optimized by this, no matter what you do with the storage, because they aren't storage I/O constrained to begin with. NVMe flash, however, could be seen as, in the context of virtual machines, as simply increasing the price of a hyper-converged appliance. That would be unfortunate, but that is very much how it might be treated by a smaller firm that's looking for a low-cost HCI appliance. However, in the future, we're looking at in-memory databases. This is like all the rage right now, and I think we're foolish if we disregard it. In-memory databases have tended to be, they were originally advanced by some of the cloud folks. They wanted to take analytics databases and put them in memory. And analytics database is kind of an interesting creature, because it's primarily it's an application for database technology that results in really not a lot of writes, but a lot of reads, and doing it all in memory would allow us to use flash for what its real strengths are, which are reading data. You can create a very strong read buffer. So if you did DRAM for your writes and then used flash for the reads, and created an appliance in a pizza box size server that you were able to put an in-memory database on, it could become another kind of hyper-converged infrastructure appliance, one that's designed specifically to host a database. Now, SAP isn't content to just do analytics processing and in-memory. They're now trying to use in-memory databases as sort of the architecture for all databases, including online transaction processing, which is a more challenging task. But again, if they're successful, it could spawn an entirely new class of HCI, an entirely new class of server architecture, if you will, that leverages dense DRAM and NVMe flash buffers for all data. And when you think about it, you could, through NVMe bus extension, enable a Lego-style approach for scaling bad environment. So if you completely exhausted all the ports and all the spots on your bus for connecting up flash and DRAM on one pizza box, you could attach another pizza box and another pizza box and another pizza box. You need to add 50 more users to your database, throw in another HCI appliance, etc. This is kind of a Lego building block model that has a lot of real potential, and you're seeing a lot of activity around this. In fact, within the last year, we've seen the generation of another specification called NVMe over Fabric. And this is basically an architecture for enabling NVMe style flash memory connectivity to be placed in a scalable fabric architecture. SCSI itself may be too slow in the future to handle all the traffic that's running between different instances of flash storage. So what they're thinking now is that we might be able to take NVMe and supplement it with various flavors of protocols that are designed specifically for memory, and then basically deliver it with some IOQ control and transport bridging, and we'll be able to connect all these pizza boxes together and create a highly scalable infrastructure. There are a lot of different ways to do it that are in development right now, different methodologies for doing the connection, iWarp and InfiniBand and ROCC, you might have heard of, and of course, as I stated in an earlier webinar we've done together with StarWind, even 100 gigabit Ethernet, which is coming down the pike as fast as you can imagine. Another highly robust methodology for networking together multiple machines and hopefully expanding the universe of silicon storage that's available in an affordable and scalable way. So it's kind of exciting stuff that's down on the horizon, and let me just conclude with some very, very hasty little statements here. First of all, by itself, NVMe is just another way to connect flash storage to servers. There's really nothing to see here. It's more efficient. It's designed really for flash memory rather than proxying flash in via a disk drive controller. Secondly, I would conclude that the use cases beyond the supposed benefits of higher throughput and lower latency for SATA-constrained applications are really few. Frankly, in my experience, very few people are saturating the SATA bus as it stands right now. So this need for speed may not be something that's widespread at this point. It might be more a shiny new thing that attracts some users to it. But going forward, there will be a purpose for this as we see especially the advent of more in-memory databases and the desire to connect them up with very robust interconnects to deliver a highly scalable all-silicon engine for doing transaction processing. And basically, I think that we ignored at our own peril. I think as engineers, we probably need to pay fairly close attention to what's going on, not necessarily because it solves an immediate problem, but because it may be architecturally significant going forward. Now, I appreciate everybody taking their time for this brief little chat. I hope there was something useful in it for you. If you have any further questions and you'd like to reach out to me, feel free. Here are all the connections. And again, my thanks to StarWind Software for having me out today, and it's been a real pleasure. Thank you.